Hi there, welcome to your lesson on the sine rule. You may know already that when we have a sine curve, it looks like this. When you graph sine of x, it's going to be this periodic function up and down like a wave. So here's a great pun on that. We have y equals sun x instead of sine x. And you can see, we know when the sun travels across the sky, it travels like that because of the way the Earth rotates, and so on and so on. So we have a sine wave. Anything that's periodic, just like the sun going up and down during the day, anything in the world that's periodic, tidal waves and things like that, all these things follow, can be modeled using a sine curve. But this lesson is not about the sine curve, it is about the sine rule, which has more to do with triangles. Let's get into it. This is a big idea in mathematics. Let's go back in time for a moment to right triangles. In the last unit, we looked at right triangles and we looked at how powerful they are in solving certain problems. For example, when you have a right triangle, most people first think of the Pythagorean theorem. And we know that as a squared plus b squared equals c squared. We can only use that rule when we have a right triangle. Also, when we have a right triangle, we can use our three basic trig ratios, sine, cosine, and tangent. Again, those only work for right triangles, but they do allow us to find parts. We can use Pythagorean theorem when we know two sides of a triangle and we want the third in a right triangle. And we can use trig ratios when we know one angle and one side, or maybe two sides and we want an angle. So these things allow us to work with right triangles. But what's the sine rule? Well, before that, let's look at this first. So in this one, this is a right triangle. Let's solve for side B. Let's see if you can do that. Well, since it's a right triangle, and we know an angle and a side, we know we have to use trig ratios. The Pythagorean theorem would not work here because we only know one side. Well, hopefully you set up the right trig ratio, and in this case, tangent. Tangent means we are going to look at the opposite side over the adjacent side, and that's what we have here, 14 over b. If you solve that for b, b goes here, tan of 32 goes down here. If you solve that on your calculator, you get an answer of 22.4. So that was easy. Right triangle using trig, easy. How about this one? Solve for side B here. I hope you didn't try to start calculating stuff here because this one is not like the last triangle. The last one had this right angle marked here. This one does not. Even though this looks like it may be a right angle here, we don't know for certain. So we say, hey, not a right triangle. I can't solve it. Or can we? That's the question for today. If we have non-right triangles, can we solve them? So that brings us into trigonometry of non-right triangles. Right triangle trigonometry can be used to solve problems involving right triangles, as we just saw. But many geometry problems involve non-right triangles. For example, this triangle here. We know two angles, we know a side here. It's not a right triangle. Can we solve anything in there? Do we have any rules for that? Well, that's what this lesson is all about. Let's get into it a little more. So back to the one we just saw. We can see this is not a right triangle, but we can make it a right triangle and use the pieces we know. And the easiest way to take a non-right triangle and make it a right triangle is to drop what's called an altitude or a height line. So I drop this line down and I'm going to say that's a right angle here. Now I have like two right triangles, and those two right triangles will allow me to solve for things. If we're back to right triangles now and we want to solve parts, we need to know at least two things. In this triangle here, because we're trying to solve for B, remember, do we know two things about this triangle? No, all we know is one angle. So if we know one thing, we're stuck. But in this right triangle, on this side, do we know two things? Yes, we do. We know this angle, we know this side. If you know two parts, you can get other parts. So let's use these two parts to find the height, because the height is actually shared by both triangles. So if we can find the height in this triangle, we can then use it in this triangle. So try it, find the height here. All right, in this case, to find the height, we can use sine. Sine is opposite over hypotenuse. I set it up here, h over 12. Solving for h is 12 times this, and that means it must be this value here. So now we know the height is 10.6. Now use that value in this triangle to solve for b. All right, using sine again, sine is opposite that height that we just found over hypotenuse, which is the b side we're looking for. Solving for b here, we can rewrite it like this. All right, so you see how we took a non-right triangle, made it into two right triangles, and it allowed us to solve something we needed. Now, that is one approach, but this approach actually leads to a shortcut. It leads to a shortcut called the sine rule. And that shortcut allows us not to go through this whole series of steps, but to actually get to that thing we need much quicker. So let me show you how it works. Okay, so let's take some notes. Here is how we're going to generalize that. So we have sine b over b equals sine c over sine c. This is part of the sine rule. But first, before revealing the whole sine rule, I mean, I've revealed part of it here, we are going to see if we can show that in this triangle. So draw this triangle in your notebook, and let's see if we can show this is true. So first, just as we did before in the last one, we're going to draw a height line or altitude, show it's a right angle, and now we're going to use the two little right triangles to see if we can get to this place. Okay, first let's begin in this triangle here. Okay, so there's the height line. I'm going to say that sine of this angle, angle C, because we're trying to prove the sine rule here, so I'm going to begin with sine. Sine of angle C is h over b, opposite of our hypotenuse. Great. Rewrite this now in terms of h. So h equals b times sine c. Okay, try that same thing in this other triangle beginning with angle b. Okay, hopefully you came up with this. Sine of angle b is height again over c this time, opposite of our hypotenuse. Rewrite that in terms of h like this. And now, since both of these two things are equal to h, in other words, those are two different ways. From this angle we can get h, and from this angle we can get h. Two different ways. Those both will give us h though, so we can actually set these two things equal to each other, like this. C sine b equals b sine c. And now that can simply be rewritten like this, because we can divide by c here and it ends up on the bottom here, and divide by b here, it ends up on the bottom here. So if we do that division, that b goes there, that c goes there, we have this. We have shown this here. And this is actually the sine rule, the rule that's going to be our shortcut. This rule will allow us to avoid having to draw this height line and create two right triangles, because this rule creates a relationship between two angles and two sides in a non-right triangle. Let's see how it works. So here is the law of sines. You should definitely note this down. It is a rule that allows for the solving of sides and angles in triangles using sine, even if the triangle is not a right triangle. So we have a non-right triangle here. There's our sine rule. Notice it's exactly what we just saw, except there's three parts here, because the relationship holds across all three angles. So before we looked at it just as two parts, but now you can say, well, sine A over A equals sine B over B equals that. The relationship works across all three. And basically you say sine of some angle over that side across from it is equal to sine of another angle over the side across from that. So that idea of going across the triangle is important here. Let's take a look at it here. So again, when you set up the sine rule, it's always one angle and the side across from it. Or in geometry, we say the opposite side. And then we can make a relationship between two others. Okay, sine of that angle and the side across from it. And sine of this angle and the side across from it. So always remember that for the sine rule. That's what we have. The sine rule, however, can be also written like this, because it doesn't matter when you have a fraction and proportions or ratios like this, if you write it top to bottom or bottom to top. So remember, it can be written either way. And each form is kind of a little more useful in different times. For example, if you have this triangle here and you want to know an angle, if the angle is the piece you want to know, then you should use this form of the sine rule. However, if you have something like this, where it's a side that's unknown that you want to know, you should use this form. Notice, again, when we want an angle, we have the angles, sine of the angles on top. And when we want to know a side, we have the side lengths on top, ABC. Okay, let's use it, because sine rule is best understood when you use it. So here's an example. We have a triangle ABC. We know angle A, angle B, and side C. Let's see if we can draw that. So here's a triangle. Most important thing with sine rule, especially when you're just reading information, is to first label it, because you have to know where to put the things. Putting angle ABC wherever you want. Here I have them here, here, here. The most important thing is once you've labeled the angles, you then put the sides appropriately on there. So across from angle A, opposite is side A, and across from B is side little b there, and across from angle C is little c. Once you've labeled that, you can label what you're given. So angle A is 65, angle B is 30, and C is 13. So again, that C is really important, that it falls between these two angles. It has to be that side. It can't be any other side, because it has to be the side across from angle C. Okay, so the next step, once you've labeled your diagram, is to decide which sine rule we're going to use. In our case, we're looking for side A. And when we're looking for a side, we're going to use this form of the sine rule. The reason for that is because in this one, the sides are along the top of the fractions. You could use this, but we're going to choose this only because when we start doing the solving after, it's easier to solve when the thing you're looking for, the unknown, is on top of the fraction. That's all. That's the only reason we choose one sine rule or the other. So let's choose this sine rule. Now, let's show things for the sine rule. Remember, we're always looking for things that cross from each other. So we have this angle, and we're looking for the side across from it. Great. And then we know this side, and oh, we don't know this angle. Okay, so we're kind of stuck because for B, we're also stuck. We don't know side B. So we are missing a piece of information, because if we set up the sine rule with this and this, we have A unknown, but we also have this angle unknown. But the good news is we know in triangles, the three angles always add up to 180. So we can actually decipher this angle right away. And that's another piece of advice I'll always give you. If you know two angles in a triangle, right away, just go ahead and fill in the third angle. So what should it be? Well, that angle should be 85 if you calculated that. Now that we know that, we can set up the sine rule. We can see we're looking at angle A, side A, and angle C, side C. So we're going to use angle A, sine A, angle C, side C. We're going to use that as our sine rule. With the sine rule, you never have to write all three things. You just write two of the three, and you set them up equal to each other. So A, we have A, side A over sine of 65 equal to side here 13 over sine of 85. We've created an equation with one unknown, which means we can solve it. In this case, to solve it, we're going to multiply by sine 65 over here. Here it is. And then we have A equals that. So calculate that. Our answer is 11.8. Let's try another one. Okay, so here, triangle QRS, and we're given some things. How about you draw this triangle, QRS, and then label the angles, Q, R, and S, and label the sides opposite each one, small q, small r, small s, and see if you can label it correctly. Okay, here is how I drew that triangle. Notice angle S is obtuse, so I needed a big angle here, greater than 90 degrees. I've labeled everything I'm given here. Okay, here's angle S, here's side S across from it, or SR, which one is that? QR, right? And then we were given SR, which is like side Q right here. So check your triangle first. Did you draw it correctly? Did you put everything in the right place? Now let's decide if we're looking for angle Q, which is here. Okay, so I hope you've given it a try, picked out the correct sine rule. We're looking for an angle, so we're going to use this form of the sine rule because it's easier when the angles are on top then, the things we're looking for. And let's see if you write the correct equation. So setting up like that, and first of all, maybe you're like, hey, wait, this is A's and B's, and this is Q's, R's, and S's. Doesn't matter, right? The relationship still holds. We know this angle and the side across from it, and we know this side, and we need that angle across from it. So you write an equation for those two things across from each other. So sine Q over 6.5 equals sine 125 over 15. Now we're solving for sine of Q here. We need Q actually. We can multiply by 6.5 on this side to get rid of it here also. And now remember, when we have sine of some unknown angle, we have to use inverse sine. So we're going to say angle Q is the inverse sine of all of this. So solve that in one step on your calculator. Let's see what you get. 20.8 degrees. I hope that worked out for you. Now make sure you study these last two examples carefully, because there are two solid examples of how to use the sine rule to find a side and then an angle. Let's try some more. Try both of these. Now that you've taken those two examples down, let's see if you can find y here and then angle x here. So again, one we're looking for a side and one looking for an angle. Try your best. All right, check your work on that one. See if you got it to work out. Sine rule has been set up. Try the next one here. Okay, in this one, there's our sine rule. In the end, we can find an angle here. So double check your work. You should be feeling better about the sine rule right now. Let's look at some more. Look at this problem here. It's a little bit of a word problem. We have everything we need. See if you can find the length of the bridge AC, which is from here to here across this lake. All right, here I set up a sine rule, but you can see I have two unknowns. AC is unknown, sine C is unknown. Oh, but good news. Remember, we can always find the angle. If we have two angles, we can find the third one. So here's the rest of the work there. Hope you were able to figure that out. Try this one here. Okay, this one's a little tougher. Let me see if I can get you started on it so you can get to a solution here. It says two people at points A and B observe a sailboat at position C. So imagine these people are standing on the shoreline or like the beach and they're looking out to sea here. Okay, it says the distance between the people is 20 meters. The first observer measures an angle of 65 as they look out, and the second observer measures an angle of 42 degrees as they look out. So everything is marked on here. And it says, find the distance from C, which is the boat, to the shoreline AB. First of all, how many ways can you find the distance from C to the shoreline? Well, I hope for that one you're thinking, like, there's kind of like infinite ways, right? You can measure the distance from C to the shoreline directly to this person, or C to the shoreline directly to that person, or any other connecting segment that you could draw. You could draw infinite lines or segments connecting to the shoreline, right? So which one's it talking about? When it says find the distance from C to the shoreline, what's it talking about? Well, here's the thing you should know. Whenever you're talking about a point and a line, and you want to find the distance from that point to a line, in this case, this shoreline. In geometry or mathematics, that always means the shortest distance. And the shortest distance, would it be this one or that one? Well, we can see CB is longer than CA, but is there even a shorter distance from C to the shoreline? Well, there certainly is, and we'll take a look at that in just a second. But first of all, something I mentioned before is when you have two angles in a triangle, you should always, first thing, mark the third angle, because two angles help you get the third one. 180 minus those two, that's what we're doing here. What's angle C? 73 degrees. And now that we know that angle, let's get back to the point I was making before, which is the shortest distance from C to the shoreline is this distance. It is always the perpendicular distance. So if you can draw a perpendicular line like that, that's always going to be the shortest distance. So that's our goal here, to find that red line, that one right there. Okay, but let's begin with what we know. Can you use the sine rule to help you? And let's focus on, working in this kind of side of the thing. So I'll give you a hint. Find the length of CB. Can you find the length of CB using the sine rule? All right, here we go. Yeah, CB or BC over sine of 65. Okay, we're using the black triangle right now. We're ignoring the red line for a second, just using the original triangle, which is not a right triangle, right? So we set up the sine rule like this. That allows us to find BC, which is 18.95. And now that we know that that is 18.95, can we find this distance, the red line that we were talking about here? In this case, you have a right triangle, so you can go back to just regular old trigonometry, sine, cosine, or tangent. So which one? Well, in this case, sine of 42 degrees would work just fine with opposite, the side we need, over hypotenuse, the one we just found. There you go. So a combination of sine rule and then trigonometry with a right triangle. Now let's talk about something else for our last problem. Let's say we have this image here. Hey, Captain, we are bearing 58 degrees. Maybe you've heard this in movies with boats. What does this mean? Okay, bearings have a very specific meaning. Let's take a look. Bearing is direction of travel. For example, here, we can say that this arrow is pointing at a bearing of 40 degrees, which means 40 degrees from north towards the east. Okay, bearings, you should know, are always taken from beginning at north and turning clockwise away from north. All right, so you begin pointing north and then you go how many degrees it says. So here we can say north 40 east or just 40 degrees. And for bearings, we often use 3 digits. We put a 0 here first in this case, because eventually we'll get to hundreds and so on, and we'll have 3 digits filled in. So how about this one? What would this bearing be? Well, this one we could say west 20 degrees south, because we're 20 degrees from west to south. But if you wrote it as a normal bearing, we'd begin at north, twist all the way around, okay? So this would be 180 degrees. And then how much more here? Well, 70, so it's 250, right? We go 180 halfway around the circle, and it would be 90 to make this right angle, but we have 20 left over, so this must be 70 here. So 180 plus 70. How about this next? Oh, I have another way. Okay, or we could say south and 70 to the west. So many ways to write it, but in general, you'll usually see bearings given this way. Okay, how about this one? What bearing is that? Okay, we have a bearing of west, 45 degrees to the north, or 315. If you came all the way around, remember from north, 180 plus another 90 plus another 45 gives us 315. Or I have another way. Oh, just northwest. Yeah, when we're directly halfway between two compass directions, we can just say northwest. How about this one? What's this bearing? Well, writing it this way, north 35 east, or just 35 degrees, because that's 35 from north. How about, let's see, oh, east 55 north also, east 55 degrees to the north. All right, one more. How about this one? We have a bearing of east 20 degrees to the south here, because this would be 90, and then 20 more to make 110, or just 110, because it's 110 from north. Now that you have a feeling of how bearings are given, let's look at, oh, I thought there's no more, but there's one more here. We are going here 270 degrees, so our bearing is 270 degrees, or just due west, of course. Okay, so here's the problem we have. A ship S is on a bearing of 120 degrees from port A and 42 degrees from port B. The distance between ports A and B is 15.2 miles. Okay, this one needs to begin with a diagram. See if you can diagram this, and let's, I'll give you a hint. Ports A and B are on the same vertical line, so they're like directly north and south of each other. See if you can draw a diagram. Okay, let's try. So we have port A here, and the ship is on a bearing of 120 degrees from here. Remember, the bearings always begin at north. So we draw a north-south line like this, and now imagine spinning an angle from this line, spinning the angle 120 degrees. So you're going to go beyond a right angle, a little bit beyond something like this, because that's more than 90. There's a 120 degree bearing. So that means a ship from this port is somewhere over here. And now from port B, it is at a 42 degree bearing. So I'm going to put port B here, and now I'm going to imagine spinning an angle from north. North is up. 42 degrees. So 42 degrees is not about halfway to 90 roughly, and then that is the ship is on that bearing. So that means the ship must be over here. I labeled it S. The distance between the ports is 15.2, and now you have everything you need to solve for the distance between the ship and each port. So you need AS and you need BS here. So how are you going to do it? Let's try. First of all, that 120 tells us this angle must be 60, because those make 180. And now we have everything we need. We have a triangle with two angles and a side. We can find the other angle to start here, which is 78 degrees. And then we can set up a sine rule to solve for things we need. All right, so the sine rule is actually set up in all three parts here. But to solve, you should just do one part at a time with this, right? So for example, AS over sine 42 equals 15.2 over sine 78. That can be solved for AS. And then BS over this equaling this to solve for BS. There's our two answers. That was tougher, but that's where you should be starting to feel comfortable with the sine rule. Great job. We will see you soon.